Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. The substrate is an ortho-substituted cyclohexene, drawn as a benzene-like ring with a circle, but likely a cyclohexene or benzene ring, bearing two substituents at adjacent positions, I, a 1-bromovinyl group, C, Br, is equal to CH2, at 1 carbon and 2, a hydroxymethyl secondary alcohol group, CH, O, dash, at the adjacent carbon. Moving on to the next step. Now H is a base that deprotonates the alcohol group, O, to generate an alkoxide, O, which is a powerful intramolecular nucleophile. Moving on to the next step. The alkoxide oxygen, generated from the adjacent CH, O group, is perfectly positioned to attack the carbon bearing the bromine in an intramolecular fashion. The carbon bearing Br is a vinyl carbon, part of C, Br, is equal to CH2, making it a vinylic system. However, considering the geometry, the alkoxide attacks the sp2 carbon bearing the bromine, vinylic substitution, or the reaction proceeds via an epoxide 3-membered ring intermediate, ultimately forming a 5-membered oxygen-containing ring, the hydrobenzofuran skeleton. And for the final step, the intramolecular cyclization of the alkoxide onto the CBr carbon displaces bromide and forms a new CO bond, creating a 5-membered ring, furan ring, fused to the benzene cyclohexene ring. The is equal to CH2 group becomes is equal to C, CH3, or remains as exocyclic alkene is equal to CH2 becoming part of the ring, resulting in a 2,3, the hydrobenzofuran system with an exocyclic methylidene or isopropylidene group. The product is a dihydrobenzofuran with A is equal to C, CH3, substituent matching option B. Option A, simple hydrolysis replacing Br with OF would give a diol, but intramolecular cyclization is strongly favored when a nucleophile and electrophile are on adjacent carbons. Option C, this would require a rearrangement to give an allylic alcohol without cyclization, which is not the expected pathway under basic conditions. Option D, a 6-membered ring, chromine, would require a 1,3 relationship between the O and CBr, but here they are on adjacent carbons, 1,2 relationship, which favors 5-membered ring formation. Therefore, the correct answer is B. Therefore, the correct answer is option B.